Welcome back. The first approach to doing differentially private ERM we're going to talk about is going to be output perturbation. So this is the idea is we're going to compute something non-privately, then add noise proportional to the sensitivity to perturb the output. This is essentially what we've seen the entire class in terms of general algorithmic idea. So this was introduced by a few different folks at roughly the same time, but the one that we'll cover, the perspective rather that we'll take today is the one of Chowdhury, Monteleone, and Sarawate, in a paper in 2011. So we'll call this CMS 11. Now, right, all we do is compute the answer non-privately and then add noise proportional to the sensitivity. The issue is that, as we saw before, the sensitivity could actually be quite high. Like we saw in the sort of SVM example, if you just change 1 point, that this could result in the hyperplane changing significantly. And similarly, when you're doing computing the median, then in this case as well, changing a single point could change the could change the answer rather drastically. So the point is that without further restrictions, we might actually have a significantly a large sensitivity, and therefore output perturbation would have to add way more noise than would actually give a meaningful result. So in order to get around this issue, we're going to talk about something called regularization. Regularization is a popular technique both in even in the context of non-private machine learning, and I'll show you one example why right about here. So the idea is, though we've seen a few examples where the parameter vector theta is sensitive to the input data set, let's just give one more example in the setting of what's known as polynomial, oh God, I can't spell right now. Polynomial regression. Where let's suppose we have a data set which is in R squared, so that is xi, yi is in R squared. And we want to essentially fit a data set using a polynomial of, say, degree k, using the squared loss. So we'll have L of theta x y being equal to the following. So from summation from j is equal to 0 to k of theta sub j times x to the j minus y squared. And so clearly, if you see this, then the theta is in r to the k plus 1. So yeah, this is known as sort of polynomial regression, where you can kind of see why. We're choosing the coefficients of a polynomial in order to find the way to best fit the value of y. The associated predictor I'll just mention is that we use the sort of predictor of y hat to be equal to summation of theta j x to the j. Sum is over j equals 0 to k. Okay, so like this is one natural way to do it, and the question is, how do you choose this k? Like, what should k be? What degree do we need to really fit the data set well and also generalize? And maybe you just have no idea. You don't know what your data set looks like, so you set it excessively high. In particular, what would happen if you set the degree, say k is equal to n? So that is you have a very high degree polynomial, one which has is of degree equal to the number of points in the data set. What could happen is that if you do something like this and you try to solve this optimization problem optimally, then what you could get is something like the blue curve here. So let's zoom this in a bit, actually, because it's small. But yeah, imagine your data set is these points, the red points. So these are the xi's, yi's. And the idea is that these points, if you don't do anything further, then the solution will be this blue one here, which you can see fits this data set perfectly. It'll get empirical risk. The empirical loss will be 0. All of these L theta XYs will be 0 because it goes through all of them exactly. But you can see also that it's kind of unnatural, right? Do you think, if you're seeing just these red points, do you feel like this blue curve here is actually like a good way to fit it? Maybe is that the real function? And the answer is perhaps not. That we kind of we generate some sort of extreme looking curve. So the good part about this is that we got an excess empirical risk of 0, but there's a few downsides. If we just forget about privacy, we're not concerned about privacy for the time being, let's say, we first have the issue that this overfits. Like, for example, it says, say if the points are here, then a reasonable new point that's in red would be perhaps over here, something like that. Now you can see that this is kind of in line with the other points, but you can see that this blue curve gives an enormous error, and so it would be very wrong on this new point. It doesn't seem likely that a point would be anywhere near this blue curve at some points like here. So one issue with this solution is that it doesn't generalize. Poor generalization. And the other issue, which is kind of, if you think about it right, actually even the same issue, but the fact that this is kind of a very sensitive solution to the data set that we have. For example, if you just removed, say, this point, then the polynomial would go crazy and it would do something very different. It's unlikely to go through that point or even close to it. Yeah, it would maybe go, I don't know. It wouldn't necessarily go there. It maybe would go something like something more like this. So you can see that this would cause it to change a lot. It'd be highly sensitive. And maybe it would change other places as well. Like, maybe it would go something more like this instead. The point is, I'm trying to get across here is that this would be very sensitive, similar to the other solutions that we've seen already. So that's bad. But instead what we can do is in some way try to search for solutions which are simple. And this is the solution of regularization. Somehow we penalize solutions. So remember, a solution is a vector theta. So we penalize solutions which are somehow complicated and try to go for things which are simple. So the way this is often expressed is the following way. L theta d is equal to, say, the summation of the loss function. So this is what we had before, theta xi yi. But now what we do is we add on lambda times n of theta. So what this is here is this term here, and theta, you can see is a function which depends only on the parameter vector theta. So it kind of ignores the data set and just says, okay, we're going to try to prefer things which have a small value of this function n. So you can see, importantly, like I said, is not dependent on the data. And this lambda here is going to be something which indicates how much regularization you want. How much do you care that your data optimizes this quantity versus actually minimizing the loss function itself? And you can see that if theta or lambda is equal to 0, then this corresponds to a non-regularized setting. On the other hand, if lambda is equal to infinity, you're going to essentially ignore the data set and just try to minimize this regularization term. So yeah, those are kind of the two extremes, and usually we'll pick some lambda that's between those two cases, significantly between those two cases. So what type of how would we regularize? Well, a common way in doing the, say, polynomial regression is to choose something which minimizes the L2 norm of the coefficients. In particular, choosing this to be summation of x sub j squared. And we really want to, say, minimize this summation. This prevents the solution from varying wildly due to the addition of a new training example, as how much theta can vary is held back by its requirement to have a small L2 norm. So you can see here in this picture, by the way, I should credit this picture to Wikipedia user Nico Guaro. You can see that the green solution is here is the regularized version. whereas, like I said, the blue one is non-generalized, is the non-regularized version. And this kind of fixes the two issues that we had before, in the sense that the first thing is that this has much better generalization properties, or at least we speculate. For example, if you have another, it seems like this is the better fit to the points, and if you have another point which lies anywhere near this, it's likely to have a small error on it, as opposed to the blue curve. And the other thing is it's fairly insensitive. You can see that if you remove this point, then the same solution would still be a pretty good fit to everything else, and it wouldn't be so unreasonable to have. So yeah, it kind of fixes both of these two issues, at least intuitively when you eyeball it. Of course, it's not formal, but it turns out that it can be formalized, in fact. And this is what leads to the following lemma in CMS 11. It says the following. If we have some technical conditions on N and L, that is, we say, in particular, we want N to be differential, the regularizer to be differentiable and also strongly convex, not just convex, but strongly convex. And we have that the loss function is convex in one Lipschitz. Then, well, these are really just technical conditions, but really the key part is for all parameter vectors theta, we have that the L2 sensitivity of the arg, sorry, this shouldn't be for all theta, it should probably be for all d. But yeah, really we're saying that the L2 sensitivity of this function, which computes the arg min of the over theta and c, will be at most 2n over lambda. So I'm not going to prove this for today. It's not really too hard. You just have to exploit the properties of n and L, and it's a little bit mechanical, a little bit tedious. But yeah, if you're interested in the proof, check it out. But really, all this says is like the classical sensitivity bound that we really wanted so much. In particular, like we just bounded the L2 norm, the L2 sensitivity of the function that we compute. So at that point, you can just add Laplace noise to the result. Stated otherwise, all you have to do is compute theta tilde equals arg min over theta in C of L of theta comma D. We know that the sensitivity is small. Sorry, like I guess this shouldn't really be for all D, because it's kind of like the sensitivity with respect to D. Yeah, so this should really just say the global L2 sensitivity, let's say. But really, we just computed some sort of function, which we know has small L2 sensitivity. So then we can add, we can output theta hat equals theta tilde plus B, where B is some like noise. So for example, you could choose B distributed as, say, like N0, and then with O of, say, N squared log 1 over delta over lambda squared epsilon squared times I times d by d. And this would imply, yeah, this would imply, epsilon delta dp, which we've seen so many times before. So yeah, this is kind of and let me note that I gave the example of polynomial regression, but this didn't require us to be doing polynomial regression. This is really more general. It just says all we need is that the function is differentiable and strongly convex, and sorry, the regularizer has these properties, and that L is convex and Lipschitz. Then we have this L2 sensitivity bound for whatever problem we're actually looking at. So yeah, that's nice. That's convenient. It essentially says that regularization allows us to add noise to the output, and that'll work. So that's great, and that's effective. It's not always the best approach. We'll see something in particular. It's not generally the most practical. It's quite quantitatively, it gives you kind of weak guarantees in some places. So we're going to see some other approaches. The next step is objective perturbation, which was also introduced by Chowdhury, Monteleone, and Sarwate, but it's kind of qualitatively different from pretty much everything else we've seen so far. In particular, how does it differ? Well, it's going to be a different type of noising. In particular, we add noise to the objective function rather than to the thing we compute. So like this might seem a bit weird, but let's recall, let me just write this one more time. Before, we might have something like L on theta D. What is the loss function? We just have, say, some summation L theta xi yi. And then we have, say, some regularizer, which maybe looks something like this. This is pretty much the same thing we used before. So this is like what we had before, but what we did in the previous case was we just solved this. We found the optimizer, we found the argmin of this, and then added a noise to it. But now let's instead the main idea here in objective perturbation is to randomly perturb L. In particular, now we have a new loss function, L priv, we'll say. I mean, the loss function is not private, but we'll see what I mean by this. And this is going to be essentially the same thing. First of all, we have summation of L theta xi yi plus the same regularization term. But now, plus the inner product of B and theta. So this essentially says we add a random term to the objective function. So B is either gamma distribution, which is another distribution we haven't talked about in this class, or say Gaussian. And this is, if you do it gamma, if you want it to be this overall thing to be pure dp and Gaussian to be approximate dp. But essentially, like the recipe is fairly simple. All you have to do is perturb, in order to apply objective perturbation, all you do is perturb L to get L priv. And then you just solve L priv non-privately. And that's it. The claim is that if you do these two steps, then this will be, the resulting answer will be differentially private with respect to the original data set. And the proof is a little bit even more, it's more technical. We're not going to go get into the proof of this. It's more technical than the output perturbation algorithm. And it's kind of like, it's tricky because you really have to reason about the optimization landscape of this perturbed function under neighboring data sets. It's not something which we'll cover here, though. If you study it, you should be able to get it, I think. But yeah, not something we're going to cover in class. So yeah, this is kind of cool. This, as stated, isn't the most practical. Why not? There's a few reasons it's not too practical. One thing is that, like, there's a few drawbacks. Kind of one drawback, which I'll mention, is that it requires really exact optimization. What do I mean by that? Well, what we needed is, like I said, we solve L priv, this perturbed function. We solve it exactly. We find the exact optimum of theta. We find the theta star which exactly optimizes it. And the claim is that finding that exactly is going to be differentially private. Now, there's many, many reasons why we are never going to, okay, maybe not that many, but there's like at least two reasons I can think of why we're not going to be able to find an exact optimum. And there's let me tell you those two reasons. The first one is that numerical precision. For example, if you're running on a finite computer, which I'm sure all of you are, any algorithm you run is susceptible to issues regarding issues related to the fact that your computer can't represent every possible number. It only has a finite amount of bits in order to represent most numbers unless you use arbitrary precision arithmetic. But that'll still cause problems. For example, maybe you might have an optimization problem where the correct answer is irrational and so on. Yeah, but essentially due to numerical precision issues, you're never going to be able to find the exact answer to any of these optimization problems. You might be thinking that, okay, this isn't such a big deal, right? Like, so what if it's close? You know, so what if maybe there's just a small amount of error? It can't be that big a deal due to numerical precision. Well, actually, it can be an issue. It wasn't shown. For example, there's a result, a paper by Mironov in 2012, which says that, it says that even for the Laplace mechanism, just adding Laplace noise, if you do this naively on a sort of standard computer, this will be susceptible to attack. And you really have to use more careful methods if you want to avoid these types of attacks. So these are real issues which actually arise in practice, and one has to be careful for these things. Another issue with the fact that we need an exact optimizer is the fact that there's also the issue that most optimization procedures, non-private optimization procedures, we haven't really talked about how we solve these problems non-privately much yet, but many of them are iterative in nature. For example, gradient descent. The way it works is that it'll start with some weak solution and then take a step and get to something which is better and better and better and better, and eventually get very, very close to the exact solution, but it'll never actually reach the true solution. And yeah, the idea is that for any finite number of steps, you still don't have the guarantee that you found the exact optimum. So that's kind of worrying because it's only guaranteed to be private if you find the exact optimum. So this is rather non-practical for both of these reasons. However, there have been some more recent works, which I sort of mentioned in the lecture notes, which you can check out if you're interested, which relax this by changing it to only be approximate optimum. In particular, you don't actually need to reach an exact answer, and anything close to the right answer is going to be good enough. In particular, and that'll be good enough for iterative methods, say like a gradient descent type approach would be just fine in that type of setting. So with improvements like this, it can actually be shown to, like, objective perturbation can actually be shown to be quite practical in some settings, in particular for like convex optimization problems. This gives us some of the best method that we currently know about. And yeah, I'll refer you again to the notes for reference on that. Additionally, they kind of have restrictive assumptions. In the sense that, it requires a lot of things about the function and needs it to be appropriately convex and Lipschitz and all this. But it turns out that a recent result by Neal et al., which appears, again, linked in the notes, this shows that you don't necessarily need all of these restrictive assumptions, and you can actually get privacy and accuracy in more general settings, say even non-convex settings. You can still prove that you get accuracy at least. Or sorry, no, you can prove privacy, though accuracy is still something they don't cover. So yeah, this seems like a rather promising direction, especially with some of the recent breakthroughs, and it remains to be seen whether these approaches will prove applicable for modern large-scale machine learning settings. That's two of the approaches, objective perturbation and output perturbation. In the third and final part of this lecture, we're going to move on and talk about one of the most popular methods for private machine learning nowadays, which is based around gradient perturbation.